What has this aircraft in common with this jet fighter? The answer might surprise you. Hi, my name is Magnar Nordahl. I'm an airline captain with interest in aviation history. In this video, I will present a real classic, the Havilland DH.82A Tiger Moth. First, we will look at the history and the design, and then I will explain how it is to fly. And then I will reveal a secret about it. Enough said, let's start. Geoffrey de Havilland was born in England on the 27th of July 1882. He became an engineer and started building cars and motorcycles. Then he became interested in aviation and designed his first airplane, which he called the biplane number 1. The first flight took place in 1909, and it was very short because one wing failed shortly after takeoff. Geoffrey was lightly injured, but that didn't stop him. He built a second airplane, the biplane number 2, which he flew successfully the year after. And Geoffrey used this to teach himself to fly. And later that year, he joined the Royal Aircraft Factory, RAF, which bought his aircraft for £400, and the aircraft was redesignated RAF FE1. In 1914, de Havilland became chief designer at Airco and designed many airplanes. The most successful types are DH4 and DH9 light bombers. After the First World War, they were used for commercial operations in Europe and many other parts of the world. The US Post Office, for example, used the DH4 to carry airmail until 1927. In 1920, Geoffrey formed the de Havilland Aircraft Company, and from then on, he never looked back. De Havilland became famous for a series of light aircraft with Moth in the name. DH.60 Cirrus Moth, also Gypsy Moth or Janet Moth, depending on the engine. And then the DH.82 Tiger Moth, which we'll look at today, the DH.83 Fox Moth, and the DH.87 Hornet Moth. The DH.60 Moth became very popular among flying clubs and private owners. The Royal Air Force was less enthusiastic and ordered just a handful of them. The biggest issue was that the access to the front cockpit, which was located under the wing, made it difficult for a pilot to escape when wearing a parachute. De Havilland solved this by moving the wing attachment forward, and to maintain the same lift center, the wings were swept back. Other changes were increasing the dihedral of the lower wings to improve the ground clearance, installing flap doors on both sides of the cockpit, and a new engine where the cylinders are hanging upside down, improving forward visibility. And voila! The DH.82 Tiger Moth was born. This machine is the DH.82A, designated Trainer Type 10 by the Royal Thai Air Force. They have 34 of them in service from 1951 to 1961. It is now on display at the Royal Thai Air Force Museum at Don Muang Airport in Bangkok. The Tiger Moth has a length of 23 feet 11 inches or 7.29 meters, a wingspan of 29 feet 4 inches or 8.94 meters, and the wing area is 239 square feet or 22.2 square meters. The empty weight is about 1150 pounds or 520 kilos. The maximum takeoff weight is 1825 pounds or 828 kilos. To do aerobatics, the weight must not exceed 1770 pounds or 802 kilos. The construction is typical for the 1920s. The fuselage is made of welded steel tubes, the engine compartment is covered by sheets of aluminium, and the deck behind the cockpit is covered with plywood. The rest of the fuselage is covered by fabric. The wings and the stabilizers are made of wood and covered by fabric. The wings are braced with RAF wire, which is flat and therefore has less air resistance than regular wire. The shape of the rudder is a trademark for de Havilland. It was used all the way to the Vampire jet fighter. The aft cockpit is the main cockpit, as the pilot must sit there when flying solo. This is necessary to keep the center of gravity within the limits. A luggage compartment is situated on the starboard side of the fuselage, behind the rear cockpit. Both cockpits have an identical set of basic instruments. The speed indicator has an auto scale for low speeds and an inner scale for high speeds. The pitot tube is located on the right-hand wing strut. Some early models had a speed indicator on the wing strut where the wind pushes on a plate with a pointer. The altimeter is located below the speed indicator. The only gyro instrument is a turn and slip indicator, and it is powered by vacuum from a venturi tube located ahead of the forward cockpit. There are 2 venturi tubes, one for each turn and slip indicator in each cockpit. Below is a magnetic compass. To the right is the engine RPM indicator, and below is the oil pressure indicator. Some other variants might have an oil temperature indicator as well. But that's it. And believe it or not, pilots were trained to fly on those instruments under a hood to simulate flight in low visibility. The flight controls are traditional, with a control stick and rudder pedals in each cockpit. They are interconnected. There are no trim tabs on the control surfaces. Pitch trim is set by adjusting a spring connected to the elevator control. The required tension of the spring is adjusted with a lever attached to a quadrant situated on the left side of each cockpit. And this rod is connected to the trim lever in the other cockpit. The elevator cables protrude from a slot in the fuselage aft of the cockpit. Note the cable arrangement over the leading edge of the stabilizer. And as you can see, there is a double set of cables connecting the rudder pedals with the rudder. And the rudder is a bit special. Normally, when you push the rudder pedal and release the pressure, the rudder will return to neutral, right? But at full power, and if you push the pedal beyond 70% of the full travel, the rudder will, without the aid from the pilot, continue to move towards the full deflection. Only the lower wings have ailerons. They are differential, which means they move mostly up and very little down. This reduces the effect of adverse yaw. The outer parts of the upper wings have automatic slot that opens at high angle of attack. They can be locked in a closed position with a lever located on the right-hand side of the rear cockpit. When the lever is in the forward position, the slots are free. This is the position for takeoff, normal flight, and landing. When the lever is in the aft position, the slots are locked. This is the position when doing aerobatics and during taxi. Otherwise, the slots might bang in and out when you're taxiing over a rough surface, and that may damage the slots. The landing gear is a fixed divided axle type. Each leg consists of steel springs and a friction damping device. A tail skid is attached to the aft part of the fuselage. It is fitted with a shock-absorbing spring and is steered through the rudder. The Tiger Moth doesn't have brakes. The only exemption is the DH.82C, which was produced in Canada. The C model also have a tail wheel and an enclosed cockpit to protect the pilots from the elements in the winter. The fuel tank is installed between the center section struts above the cockpit. The capacity is 19 imperial gallons or 86 liters. A step on the right side of the fuselage gives access to a corrugated step plate on top of the engine cowling, and from there you can access the fillet cap. Next to the fillet cap is an overflow valve, in case of thermal expansion. At the rear of the tank is a fuel gauge. This is a glass cylinder with a floating bowl inside. A fuel cock is fitted on the lower left-hand side of the tank. It is open and closed with a lever in the cockpit, and I believe it's this one. It acts on push-pull rods from the cockpit up to the tank. Next to the fuel cock is a dirt trap and a drain valve. The DH.82A is powered by a Havilland DH.82A engine, driving a two-bladed fixed-pitch wooden propeller. It is a 4-cylinder inverted inline air-cooled engine, and it develops 130 horsepower. The engine rotates counterclockwise when viewed from behind, and like with many old aircraft, the engine is started by hand. On the right side of the cowling is the air intake for the carburetor. The oil tank is located on the left side under this bulge. The capacity of the oil tank is 2.1 imperial gallons, or 9.5 liters. The throttle lever is mounted on the left-hand side of each cockpit, but only the aft cockpit has mixture control. As with most piston engines, the ignition is provided by two magnetos. The right-hand magneto is an impulse magneto, which provides a better spark when the engine is started. There are two pairs of magneto switches outside each cockpit, which means the engine can be started with a pilot in either cockpit. And because of the location of the switches, they are visible for the person who is turning the propeller, adding to the safety. And now the big question. What does a Tiger Moth have in common with an F-16? The answer is this: the anti-spin strakes. Early Tiger Moths did not have those strakes installed, and it was discovered that the aircraft could be difficult to recover from spin. The reason is that at a high angle of attack, the horizontal stabilizer blocks the airflow around the rudder. The anti-spin strakes produce a powerful vortex that directs the airflow around the rudder, giving it better authority during spin recovery. The anti-spin strake works in the same way as LERX, leading edge root extension, which is found on F-16 and many other fighter jets. At high angle of attack, the LERX produces a strong vortex that maintains the airflow over the wing past the stall angle. This allows for the fighter to make sharper turns. The first jet fighter to incorporate LERX was the F-5A Freedom Fighter in 1959. The same principle applies to the fins you can see on engine nacelles on many airliners. They compensate for the loss of lift caused by the shape of the engine nacelle. But it was the Tiger Moth that used it first. The first Tiger Moth variant, the DH.82, had an air-cooled 4-cylinder Gypsy 3 engine developing 120 horsepower. The next variant was the DH.82A, which has a Gypsy major engine developing 130 horsepower, and this became the most produced variant. The DH.82B had a wider fuselage and a larger tail fin. Only one was built. The DH.82C was a cold weather variant produced in Canada. It had enclosed cockpit, tailwheel and brakes. It could also be equipped with skis. The US military designation was PT-24. One subvariant, the DH.82C Menasco Moth, was fitted with a Menasco D4 engine due to shortage of Gypsy Major engines. Finally, we have the DH.82 Queen Bee. This was a radio-controlled drone. It was used as a target practice for anti-aircraft gunners and had a single cockpit so it could be flown by a pilot. It was equipped with either wheels or floats. The Tiger Moth was produced at the Havilland's factory at Hatfield. In 1941, the Hatfield factory became busy producing Mosquito fighter bombers, and the production of the Tiger Moth was moved to Morris Motors in Oxford. They completed a total of 3,433 Tiger Moths. The Tiger Moth was also produced in Australia, Canada, New Zealand, Norway, Portugal, and Sweden. When the production ended in 1944, a total of 8,868 Tiger Moths had been built. The first flight of the DH.82 took place on the 26th of October 1931, and the Royal Air Force received the first units the following year. Nearly every Royal Air Force pilot learned to fly in a Tiger Moth. It served with 20 squadrons as a basic trainer, target drone, and coastal patrol, searching for submarines. The intention was to detect German U-boats and scare them to dive. But it couldn't have been much scary because the only armament was a signal pistol. The Tiger Moth was used by the armed forces in 40 countries. In addition, there were hundreds of civilian uses all over the world. The Tiger Moth is still popular, and more than 250 are in flying condition today. 3 of them are in Norway, where I am from. They are painted in the colors of the Norwegian Army Air Service. One of them has a special story, because it was built in Norway in the 1930s. It was evacuated to Sweden during the war, and it's now restored to its former glory. I have flown the Tiger Moth once, and that was more than 20 years ago. Therefore, I might get some details wrong, but anyway, here is how it is to fly. Before the flight, I was told that it flies like a Piper Cub. I am familiar with the Cub, and it didn't take a long time for me to feel comfortable in the Tiger Moth. The biggest difference is that you can hear the wind singing in the wires. I will have to cover the pre-flight and engine start procedures in a later video, because I don't have proper footage yet. Since there is no electrical system, the engine is started by hand. The engine should warm up for 4 minutes at 900 to 1000 RPM. The oil pressure should be 35 psi. The magneto check is performed at 1600 RPM, and the RPM drop should not exceed 100 RPM. When you are ready for taxi, remove the shocks. And on the grass, the Tiger Moth is fairly easy to taxi, but like most tail draggers, you must zigzag to see what's ahead of you. Therefore, you must taxi with care. And the only brakes is the drag caused by the tail skid. To make sharp turns on the ground, you will need to add power to increase the airflow over the rudder and unload the tail by pushing the control stick forward. On a hard surface or in a moderate wind, you will need a wing walker to assist you with directional control. Maximum recommended crosswind is 10 knots, and that might be a handful for many pilots. On this video, you can see the pilot starts the takeoff roll on the grass. When the aircraft enters the runway, the rudder is already effective. You push the nose down to see ahead and to reduce the drag. With the tail in a slightly down position, the aircraft will become airborne by itself. The initial climb speed is 70 miles per hour with 2100 RPM. When reaching 200 to 300 feet, you reduce the power to 2050 RPM and reduce the climb speed to 65 miles per hour. Normal cruise power is 1950 RPM and the indicated airspeed will be 70 to 80 miles per hour. With this power setting, the consumption is 6 to 6.5 gallons per hour. This gives a safe endurance of 2.5 hours and corresponds with a maximum range of 300 miles or 480 kilometers. The stall speed is 40 miles per hour with engine at idle and 30 miles per hour with power on. The Tiger Moth is a very good trainer because it's easy to fly but requires precision to be flown perfectly. If you are sloppy, it will tell you right away. For example, if you side slip more than a couple of degrees, the windscreen will no longer protect you and you will get a turbulent airflow into your face. The windscreen is also creating a vortex that flows over your head and hits you in the neck. Before you get used to the aircraft, you will rely on the slip indicator to fly coordinated. The rudder forces are lighter than in a Cub. The pitch control is similar, and the roll rate is, like in the Cub, quite slow. And since the propeller turns in the opposite direction of aircraft with American engines, you must reprogram your brain to add left rudder instead of right rudder when you add power. The speed on final approach is 65 miles per hour, and this is also the best glide speed with the engine out. For short field landings, you aim for 55 miles over the threshold. It takes practice to land the Tiger Moth perfectly. It can be landed in two different ways, 3-point or on the main wheels. A 3-point landing requires continuous assessment of aircraft altitude, attitude and speed. And you need numerous control inputs during the flare. When you reach 40 miles per hour, the stall speed, all three wheels should be 1 inch above the ground. Then the aircraft will stop flying and gently settle on the ground. You continue to pull back on the control stick and use the rudder to maintain direction control all the way to full stop. Many pilots prefer to land the Tiger Moth on the main wheels, especially in crosswind or on a hard surface. This gives better direction control during the first part of the landing roll. In this case, you keep the nose down as long as possible. And in a Tiger Moth, like all tail draggers, the landing is only completed when the aircraft is safely back in the hangar. When you get the opportunity, you should have a flight in this charming lady and get a feeling of what flying really is about. And that's all for this time. Please support my channel by sharing with your friends and all that. Thank you for watching. Have a wonderful day and happy landing.